Hello and welcome to this webinar, one of a series by Outokumpu covering a variety of aspects of stainless steel. Today we'll look at the use of stainless steel in some water treatment applications. Please note that the information we give here can only be considered as general guidance, and if you're considering the use of stainless steel, you should discuss your specific requirements and the environmental conditions with your local Outokumpu sales office. They'll be delighted to offer more tailored information. Today, first we're going to take a look at the corrosivity of water. Then we'll look at some grades that are typically used in this application area, including desalination. And we'll consider some cases of projects undertaken in places with desalination, sewage treatment and water storage. And finally, we'll summarize and draw some conclusions. But before we get into the content of today's presentation, I'd just like to say a few words about Outokumpu. Outokumpu today is a global leader in the stainless steel industry with a vision to become the undisputed #1 in stainless steel. The group currently employs over 8,000 people in around 30 countries, and our net sales in 2011 were about €5 billion. Outokumpu is listed on the Nasdaq OMX Helsinki exchange. On this side, you can see the footprint of Outokumpu across the globe. The main production sites are in Finland and Sweden, with significant operations in the United Kingdom as well as the USA. We've got sales offices across all the key markets, and in addition to the main production units, sales offices, of course you have service centres which are able to provide highly tailored product as well as being closer to the main markets. Very briefly, as you can see from this slide, we have an extensive range of stainless steel product. We supply so-called flat product in coil, strip and sheet and plate forms, and very often with sheets and plates tailor-made to quite specific customer requirements. And in addition, we produce tubes, pipes and fittings, as well as in a range of round, hex and square forms. So turning now to the first aspect of today's presentation, the corrosivity of water. There are several factors that create the risk of corrosion from water. And it's worth noting that despite the fact that water is the most common of all corrosive liquids, it's still quite hard to predict the corrosivity we can expect to find. This is because there are many different types of water with a wide variety of compositions. So for example, the corrosivity will be determined by factors such as chloride content, temperature, presence of oxidants, any biological activity, the pH value, and the actual flow conditions, as well as potentially the presence of any welding oxides left over from the manufacturing and production processes. I'd just like to focus for a moment on the first of these, chloride content. Quite simply, it's quite clear that it's the chloride content which directly impacts upon the corrosion we can expect to see. The higher it gets, the worse we can expect it to be. Similarly, temperature also has a direct impact in that the higher the temperature, the worse the corrosion we would expect to see. However, even in circumstances where the chloride levels are quite low and the temperatures we see are low, the corrosivity can be quite high due to the presence of oxidants. And these oxidants, such as chlorine, may be present in order to kill off any biological activity in the water itself. We mentioned biological activity as a factor which may lead to increased corrosivity. However, biological activity itself rarely corrodes stainless steel. Instead, it may create the environmental conditions which in turn lead to corrosion. And on this slide we can see some examples of damage from different types of corrosion. To the lower right we can see some pitting corrosion where the damage is concentrated to scattered small areas, the pits. The image to the left shows some crevice corrosion, and this is where the corrosion takes place in sealed areas, such as in this example between flanges. Stainless steel is more sensitive to crevice corrosion than to pitting corrosion, which means that if you select a grade which is resistant to pitting corrosion, we may still find crevice corrosion occurring under the deposits. In galvanic corrosion, what we find is a combination of two metals, where the less noble material is attacked by corrosion and the more noble material remains unaffected. And finally, stress corrosion cracking. And for this to occur, stainless steel needs to be subjected to both mechanical stresses and corrosive environment. And it tends to occur at elevated temperatures. So when selecting the most appropriate grade of stainless steel for use in water treatment applications, it's very important that we fully understand the nature of the corrosion type that we might find. The most common type of corrosion that we find in water treatment applications is pitting corrosion and crevice corrosion. However, we might also see stress corrosion cracking and potentially some galvanic corrosion. Now, there are indeed many different corrosion types and challenges to be found within the water treatment application, but it's important to recognize there is a stainless steel solution suitable for each and every one of them. There are also quite a few sources of help available. So this varies. A great deal of research has been carried out in laboratories, which produces tables of grades ranked according to their suitability to various conditions. And there are also engineering diagrams, which can give quite specific indications of how various grades will perform in certain applications. And a very powerful source of data is, of course, the in-plant test. And typically, this will involve the production of a rack like the one shown on this slide, which has a number of grades attached to it. This rack is then shipped to the plant site where the new installation is to be. Leaving the rack exposed to the local conditions for a specified period, subjecting the material to a precise replication of the service condition, allows us to assess which grade would perform best. This performance would be measured in both the technical and, of course, commercial terms, and identifying the optimal and cost-effective solutions. Of course, it's usually possible to look at current service experience as well and to understand which materials have been used already in similar installations in the past and how they've performed. Outokumpu's experience and R&D facilities can be exploited by our customers to help with all of the above tools and methods to ensure that you get great selection, your grade selection arrives with the correct outcomes. Of course, our specialists are always happy to discuss your specific requirements to help you to achieve this. So, now let's turn to our product and our stainless steel grade portfolio. If you look at this table, you can see some grades typically used in this application area. Now, they're arranged into two key groups. The upper grey rows depict austenitic grades, and while the lower blue rows depict the duplex grades. In the first two columns, you can see the product names according to the two different standards. The first is the Outokumpu company name, and the second is the European designation. And the next four columns show the key elements used in each alloy. And of course, what I would draw your attention to is that the duplex grades utilize far less of the more expensive elements such as nickel and molybdenum. This will of course have a direct effect on the final price of the material in question. Also, given these lower values, the price of duplex grades is considerably easier to budget as they're less susceptible to fluctuations in the raw material cost. In a nutshell, they represent both a cost-effective and a cost-stable option. Turning now to the mechanical properties, once again we've divided the table into the two key product groups of austenitic and duplex grades, and in the third column we show the yield strength of each alloy, and as you can see here, the duplex grades are typically twice as strong as the austenitic grades. On this next slide we've plotted each of the alloys against two dimensions. And on the x-axis, we plot the pitting and stress corrosion and strength on the y-axis. And the first thing to note is that the austenitic and duplex grades distribute across the pitting and corrosion scale in broadly the same range. However, when we look at the y-axis and the proof strength, we can see that the duplex grades have a clear advantage. So again, in a nutshell, what you can see here is that for each of the austenitic grades, there is a duplex alternative with considerably higher strength, and that Outokumpu has a broad product portfolio from which you can select to meet your needs. So turning now to some specific cases starting in desalination, both the good and, I have to say, the not so good. Looking at this slide, we can see an example of some high-pressure piping made from 316L. The image on the left shows a pipe that was taken out of service from the old Jeddah plant after just 6 years, and the image on the right from a similar plant in Australia. The takeaway here is that a combination of seawater and 316L was not successful. This is also true of another 300 series grade, 317L, and on this slide you can see a couple of other examples that Outokumpu has investigated from a plant in the Middle East. As you can clearly see, there's very extensive corrosion. However, some slightly higher alloy grades, the austenitic 904L and Duplex 2205, on this slide it says mixed experience, and I'll try to explain what we mean by that. First of all, both grades are commonly specified for use in desalination plants. However, although there have been a few success stories supported, we've also seen many reports of corrosion. And on this slide, you can see the results. On the left, the 904L from the plant in the Middle East, and in the center, a plant on the Canary Islands, also 904, and then Australia. Some of you involved in the seawater reverse osmosis process will have heard of the failure of 2205 at a plant in Australia. Concrete evidence that 2205 is not suitable for full-strength seawater. Turning to a different grade, austenitic 254 SMO, the good news is that I don't have any horror story pictures to show you, as there aren't any reports of failures of this grade in high-pressure piping in seawater reverse osmosis. It's been extensively used in more than 50 plants around the world, and Outokumpu has been involved in more than half of them since the 1980s. However, successful though it is, many plants are now turning to the corresponding duplex grade to 254 SMO, which is 2507. Given the high pressures involved in the piping systems of seawater reverse osmosis plants, the higher strength of the duplex grade can be utilized to achieve higher strength, while very often reducing the wall thickness and thus purchasing less material. This makes it a very cost-effective solution. This duplex grade has been employed since the early 2000s, initially in plants in Singapore and in Perth, but since then in a variety of plants and conditions around the world. So turning now to a different process, multi-stage flash, because the process is often aerated, we quite often saw mild steel being used from the 1950s, for example. Later in the 70s, because these proved to be insufficiently resistant, plant used stainless steel linings on the pipes or plate cladding. However, these solutions are quite complicated. More modern plants will typically use solid stainless steel. Initially it was 316L, but later we've seen the Duplex family brought into use. So let's look at that in a little bit more depth with a couple of examples. First, we've got the use of 2205 in the Evaporator at a multi-stage flash plant in Libya. Because of the higher strength of duplex material, some 30% less material was required. That led to an overall weight saving, which in turn led to a cost saving of around $1 million. And then we see a more advanced solution using a dual duplex installation. Because the lower section of the evaporator sees more aggressive conditions, there we see the high alloy 2205 in use. However, higher up where the conditions are less aggressive, Outokumpu's LDX2101 is used to good effect, since LDX2101 is even more cost efficient than 2205. So that the overall even greater cost savings can be achieved, way beyond the switch from austenitic. This innovation of using a dual Duplex 2205 and LDX 2101 evaporator is now the solution of choice, and we can see many successful examples of its employment in key installations around the world, as you can see here. We've seen a similar development in multi-effect desalination plants too. And in this example, you can see the world's largest MED plant in Saudi Arabia, commissioned by SIDEM in 2010, with the enormous capacity of 800,000 cubic meters per day. In this case, 2205 was again used for the lower section of all the evaporators, while 2304 was used for the less hostile conditions higher up. In the ventilation systems of both multi-stage flash and multi-effect desalination plants, we've seen plenty of evidence of failures of installations using standard austenitic grades like 316 and 317L. And this is due to the presence of chlorides and bromides in the system. The remedy has always been to replace these grades with something more corrosion resistant. And in the photo below, you see an example of from an MSF plant in the Middle East, where the two grades have been used in the same application, 316L and 254 SMO. The image speaks for itself. 316L is attacked by significant corrosion, whereas the 254 SMO is completely unaffected. Switching now to condenser tubes and tube sheets. Traditionally, we've seen titanium, copper alloys, and aluminium brass alloys being used. However, factors such as the inconsistent availability of titanium and the environmental debate about the release of copper ions into water, together with numerous reports of corrosion failures in those plants, has led to the increased usage of stainless steel because clearly it's more readily available, it has a lower environmental impact than copper with regard to metal leaching, and again, compared with copper, is much harder. So there are virtually no limitations on water velocity. There have been several examples of stainless steel being used in condenser tubes and tube sheets. 2205 in the condenser tubes in the heat recovery stages of the Aruba plant in the Dutch Antilles, as well as in the brine heater, and highly alloyed ferritic grades in the heat reject stages. Looking now at some references, you can see a long list of places around the world where we've been delivering a variety of stainless steel grades to desalination customers over the last 25 years or so. Those grades you see here have proven to be the most successful for our customers, and there are many more references as well as more detail about them on our homepage, outokumpu.com. So let's turn now to a completely different area, sewage treatment. First of all, it's clear that conditions in sewage plants are less challenging than in desalination, and for that reason we see considerably lower alloyed grades being used. And for example, there are many successful installations of austenitic grades where chloride levels don't exceed 100 parts per million. In other areas where the chloride levels are higher, typically somewhere between 200 and 400 ppm, we see engineering companies specifying 316. Duplex grades are just starting to make some headway in this area too, as a higher strength can often be utilized in certain areas to provide a cost-effective solution. Despite the fact that the processes and solutions are apparently well understood, there are areas here where extra care is needed. For example, in flocculation stages where ferritic chloride is added. Water containing ferritic chlorides can be quite aggressive for two reasons. Firstly, because of the addition of chlorides, and secondly, due to the strong oxidizing nature of these three ions. So in these stages, there is a risk of pitting and crevice corrosion if the grade is not resistant enough. In aerobic biological stages, the presence of bacteria or the conditions the bacteria produces might be harmful for stainless steel. In digesters, which have anaerobic conditions, These are usually not considered to be dangerous to stainless steel. However, if oxidants are allowed to pass into the system, conditions can become quite aggressive. So for these conditions, at least for the dosage points of chemicals, if those are used, higher alloy grades should be considered. On this slide, we see another successful application for duplex grades, and that's the collector lines for sewage plants. Traditionally, these have been constructed from concrete or fiber-reinforced polymers. However, these materials are quite brittle, and so in areas of high traffic or seismic activity, there is a strong risk of cracking or fracture of the lines. So, as stainless is a tougher and more ductile material than concrete, the argument to use it is quite compelling. However, leaving a stainless pipe underground unsupported isn't a viable solution either, and so the solution employed is a hybrid between the two. A thinner wall stainless pipe placed in a load-bearing concrete duct achieves the best of both worlds and provides a robust and cost-effective solution. In this area, duplex grades should be considered also, as they have a higher resistance to abrasion, which may be needed. As we saw earlier with the plant in Saudi Arabia, desalination plants are getting bigger and bigger all the time, and as the need for potable water grows, this in turn leads to an increased demand for storage capability from the water produced. And this is an area where duplex grades have proven to be ideally suited. The argument in its favour should be familiar by now. Because it's inherently a stronger material, we can use thinner grades, which brings benefits for the material itself, material handling, lower welding cost, less filler material, and so on. So, although the initial investment cost is usually higher for a stainless steel tank when compared with a carbon steel installation, the life cycle cost advantages are clear. For example, stainless steel doesn't need to be painted or surface treated, and it's also 100% recyclable. On our homepage, Outokumpu.com, you can find a tool that you can use to evaluate different materials by inputting your tank's dimensions. For example, the height and diameter. Then selecting the grades that you want to compare, you can quickly calculate the amount of material required for your tank. In this case, a significant reduction of over 30 tons of a material sold by weight. And as we've seen in several areas, the duplex grades are providing significant benefits in a wide range of applications and environments across the globe. And here are some pictures of a few of them. In conclusion then, sorry to say it, but stainless steel isn't always stainless. But there is almost always an appropriate grade available. And Outokumpu is here to help you make sure that you select the right grade for your application. With long experience of water treatment applications, also remember that for austenitic grade, there is a duplex grade with a higher strength. Thank you for listening, and we hope it's been interesting to you. If you have any questions, then please don't hesitate to send them to the address shown here. Thank you, and goodbye.